So suppose we have a basis. In order to talk about coordinates, we need a basis, okay? So can we get that across, okay?
So you need a base to have
We need a
coordinates.
basis.
The basis to have
Okay?
coordinates.
We always talk about coordinates relative to a basis or on a basis, right? So you talk about coordinates without specifying a basis. That means it is the standard one, right? What is the standard basis? In R2, the standard basis are the E1 and E2, right? So do you remember what E1 is? So this is E1. That's 1 and 0, right? So that's a unit vector in the positive x1 direction. And then E2. E2 is 0 and 1. That's in the vertical direction, unit vector. So that is the standard basis. Basis of R2. So for R3, you need one more, right? E3. In R3, that would be 1, 0, 0. 0, 1, 0, and then E3 would be 0, 0, 1. So you need a basis. When you say we have coordinates, that means you already have a basis. If you don't specify what basis is, that's the standard one. But we can have other bases. That's the point of this section. Suppose we use E1 still, but the other one I can take, say, E1 plus E2 divided by 2. So that's by 2 vectors. So V1 is still E1, but V2 is different. So they are linearly independent. Together they span the plane. So they form a basis. Another basis of R2. So what is the coordinate? If I give you this is E1 and V1 and V2, right? So in general, we have two vectors, V1 and then V2. They form a basis. Then what is the coordinate of a vector? So of course we need a vector, right? We are talking about coordinate of a vector. So you give me any vector, x. We'll do the following. We are going to geometrically withdraw these lines parallel to these two vectors. So we have these two intersection points. Put an arrow here, put an arrow there. Then this x is the sum of these two new vectors. I call them new vectors. Why? Because V1, V2 are there. They are old vectors, right? And this x is an arbitrary vector. We're talking about its coordinates relative to V1, V2. So we form these two dots and then form two arrows, right? Then this x is a linear combination of V1 and V2. Why? So this is not a very parallel line, right? So this is more parallel, right? So you can see this is a parallelogram, right? Okay, so x is, so this is V1, is this vector plus that vector by the parallelogram principle. But this vector here is a multiple of v1, right? It's on the direction, on the line with v1. The other vector, this one, is a multiple of v2. So we just write down as c1 v1, and this is c2 v2. And then x is c1 v1 plus c2 v2. So every vector has a unique representation as a linear combination of v1, v2. Here, c1 and c2 are unique. Unique, that is for a given x. That's unique. You wouldn't have two sets. So suppose you have d1 v1 plus d2 v2, then the c1 must be equal to d1, c2 equal to d2. So any basis has this unique representation, right? Okay, so now here comes the coordinate vector. Coordinate vector of x. Sometimes we say relative to a basis or on a basis. Or just later we have another notation. Let's just write things out first without introducing too many notations. So the coordinate vector of x relative to a basis, say v1, v2, is, so it's a vector, right? Well, because I said it is a coordinate vector, the coordinate vector, right? So it's going to be a vector. So guess what I'm going to put it in here?
C1,
Yeah,
C2.
C1, C2. Okay. So very good. So you can look at it. Yeah. They have more than C1, C2.
What's
They have
the
many because they have more vectors in the basis. Okay. So now, if you give me x, I have these coefficients forming a column vector. So here is the notation now. So be prepared, okay? We're going to throw at you some fancy letters, notations. So this basis, we use this B, right? So is this understandable? It's a B, but it's a curly B, right? For basis. So now we have another way to say this coordinate vector. In the book, they just say the B dash coordinate vector, right? So instead of saying coordinate vector of x relative to a basis or on a basis, you can just say the B coordinate vector, right? So that's the basis. So then you don't need this relative to. That's the meaning. Okay, how about this C1, C2? This coordinate vector relative to B. We have a very fancy notation. So look at this one. We use a pair of brackets around the vector x and then put the curly b as the subscript, right? So that is, so this is the b coordinate vector of x. So when you see this, vector. This could be substituted by a real vector, right? Could be 3, 5. So x can be a very concrete vector. So this vector, you put this in a bracket and then say, put a subscript b there. That's the b coordinate. See, b coordinate, the brackets. See, brackets, right? And whose coordinate? Well, x, right? So that's what they say in this box. So what happened is this: consider a basis B consisting of V1, V2, all the way Vm. So m of them of a subspace V. So you already know V has dimension m, right? And every vector is in Rn. So every vector is in Rn. And then any vector x in V has a unique, so uniquely, that means has a unique representation, has a linear combination of these basis vectors. Use C1, C2, all the way Cm as the coefficients. Then you just turn around and write them in a column vector, right? Use them as the components to form this column vector. And then we have a fancy notation for it, right? So, and the name is the B coordinate vector of x. Okay? So now, let's do a little bit more. So here we introduce matrix S. So what is this matrix S? Its columns are the basis vectors, V1, V2, all the way Vm. So they give you V1, V2. For instance, we have only 2. So we use this S. V1, so that's, so I'm not going to draw a line, you know. This is first column, second column, right? Just use the vectors in the basis to form the columns. That's S. Now we're going to do a little bit more. Look at this one here. What is it? C1 V1 plus C2 V2. This is probably the nth time with a big N, large N, that means many times. We are going to rewrite a linear combination as what? A matrix times a column vector. So can someone help me? What is this matrix?
2 by 2.
So remember we have done this many times. V1, V2, right?
V1, V2.
Okay. V1, V2. And then what is here?
C1, C2.
C1, C2. Very good. Okay, so in terms of this capital S, remember this is capital S, right? So capital S times, and what is this?
A vector.
The B coordinate vector, right? So that's the notation for C1, C2. So this is C1, C2, and then you know what that is. This is the matrix S. So that's why they say X. Remember we start out from X all the way, right? X is this linear combination, which is S times the coordinate vector. So that's what they say here. So note that X is S times the B coordinate vector, okay? And where this is S is this vector, and N by M matrix. Okay. How about an example? That's the example. Suppose we have a basis. So they look at example 1. So I'm not going to work on example 1 as in the book. It took too long. They did some geometry. So here is the beginning of example 1. Okay? So I'm going to skip this second page, and then I'm going to work out the rest. So what is example 1? V1, V2, they give you V1, V2, which form a basis, okay? So they are in R3. And then we want to find the coordinate vector of this given vector, 5, 7, 9. Well, we use X, but it is given in this case. 5, 7, 9. So we want to find its coordinate vector. So how do we do that? Just follow this scheme. We want to find linear combination, right?
So we're gonna always need to have the, we're always gonna need to have a V.
We need a
vector.
set of vectors
Vectors,
who
and then
form
you-
a basis.
And then you always need the X, because you
And
won't
then
know
we
the
give
C.
you X.
Unless they give you the C.
Right. Well, just look at this again, right? Remember we asked you to do this, right? Find this. Well, in order to answer this question, you need to give me the B, the basis. You need to give me also the X, right? So it's natural. Okay. So 5, 7, 9, so we need to write this as C1, V1, right? V1, so what is V1?
1, 1, 1.
1, 1, 1. Okay. C2, what is V2? C2, V2.
1, 2, 3.
1, 2, and 3. Okay? So once I find C1, C2, you can just use C1, C2. To form this column vector. So that is the answer. This X, bracket, and then a B. So we just need to find C1, C2. So I'm going to skip this part, right? Because we have done this so many times to solve a linear system. So I'm going to set it up for you. 1, 1, 1, 1, 2, 3, okay? And then 5, 7, 9. So that is the augmented matrix for this linear system. We need to solve it, right? So I'll leave it to you. So what they're saying is at the end you get 1, 0, 3, 1, 0, and then 3. Second 0, 1, and 2. The third one is 0. 0 row. So from here you find yourself two numbers. This first equation means C1 equals 3, right? This is 1 C1 plus 0 C2. And the second one gives you C2 equals 2. So what do we get? 3 and 2. So this vector 5, 7, 9, this is 5, 7, 9. Coordinate is 3 and 2, but it's relative to B. So what does that mean? Exactly this. This vector is C1 is 3, right? 3 times B1, so this X equals 3B1 plus 2B2. Okay? Now, let's look at the other direction. If I give you the coordinate vector of an unknown vector X, relative to a basis. How do you find this vector? Well, if you know 3 and 2, you just perform 3v1 plus 2v2, right? You're getting your 579 back. So exactly this. So you don't need to write them out like this. You can use matrix multiplication. That's the note here. So how do you find the vector x? If you know the b coordinate vector of x, then here is the formula. S times this coordinate vector. You are getting back the vector x. So either way, you use S times this coordinate vector, or you write it out like this. Okay, C1v1 plus C2v2, that's fine. See, that's what they are saying. So you can also verify that indeed this matrix 1, 1, 1, 1, 2, 3, that's S, right? Times 3, 2 indeed give you 579. Or you can just do it separately. 3 times first column plus 2 times the second column. And you are getting back 579 also. So either way. Okay. Next, we're going to go over these two properties. So coordinates is a new thing, right? You give me a basis.
What?
Every vector x has associated with a coordinate vector. So we can view this process as an operation. So getting or taking the coordinate vector is an operation, right? You give me a basis, you give me an x, finding this C1, C2, right? This operation, or finding the coordinate vector. This operation is linear, that's what they say in this box. The theorem says coordinate, taking coordinate, so say
Can't see
it's
where
a linear, it's a linear operation. So two properties. If you add two vectors x and y, first add them first, and then find the coordinates. That is the same as finding the coordinates of x and y first, then you add. So as if this b, subscript b, can be distributed to x, to y, right? So inside the brackets. So you can take this inside the bracket. Okay? How about the other one? You multiply x by k, a scalar first. Then you take coordinates. It is equal to k times the coordinate vector of x. So as if you can move the k outside the bracket. So these two properties are linear, right? Linear property. So the proof is straightforward. So suppose your x is C1v1 plus C2v2, so I'm going to stop at m equals 2. How about that? C1v1 plus C2v2. Then if you multiply this vector by k, so you just multiply the right hand side by k. That would be kc1 v1 plus kc2 v2. And then you associate the k with c1. So parenthesis KC1, parenthesis KC2. That would be the new coordinates, KC1, KC2. But then you can pull out the K. Then you have K times C1, C2, that's K times coordinate. So the other one is easily checked like this. So the first one is the same. So let's look at the example 2. How about we have two vectors, 3, 1, minus 1, and 3, forming a basis of R2. There are two parts of this problem. So you will do homework like this. In the part A, they give you the vector, say 10, 10, 10 and 10, and ask you to find the coordinate vector. Part B is in the other direction. They give you the coordinate of a vector x, 2 and minus 1, and ask you to find x. So for the first one, that's what we did. You write your x, which is 10, 10, as a linear combination of the V1, V2, C1, 3, 1, plus C2, minus 1 and 3. So you need to solve this either by augmented matrix, what we just did, right? Or by inspection. You can sometimes guess what C1, C2 are. If you guess it wrong, adjust a little bit, right? Okay. If after several tries you still didn't get it, then you can always go back to the augmented matrix, right? How about the second one? This time, it is recommended to use this formula. Use this formula. X equals S times XB coordinate. Okay? So this is the second method for part A. So it is not unique. There are two methods. So this one is based on x equals s times coordinates. To find coordinates, you just need to use s inverse times both sides, right? S inverse times x, then is the coordinate. But usually we don't do it that way, okay? Because finding inverse is not a trivial or simple path, right? Solving linear system, we have a systematic way of doing it. Okay, how about part B? That's just straightforward. Using s times the coordinates, okay? So as I said, you can use two methods also. Either write down this y as a linear combination of V1, V2. They give you this 2 and minus 1. So the first and the second components, right, of the coordinate vector, which is given. So just go back here. In part B here, sorry. So they give you this 2 and minus 1 coordinate vector. That means 2 times V1, right? And then plus minus 1 times V2. That would be your original vector x. So that's what you can do. 2 V1, V1 is 3, 1, plus minus 1 times V2, that's minus 1 and 3. So 6 plus 1, you get 7. 2 minus 3, you get negative 1. So that's how you find vector. Or you directly use this matrix S, so times the given coordinate vector. The matrix has two columns. First column is V1, right? 3, 1. Second column, minus 1 and 3, times 2, negative 1. So you multiply this out by our dot product. 3 times 2 plus negative 1 times negative 1. You get 7 back, right? Okay. 1 times 2 plus 3 times minus 1, you get minus 1. So either way, okay? So now, we want to find something called the matrix of a transformation. So another new thing. So we already have a good idea what coordinate vectors are, right? How to go back and forth from the vector itself to its coordinate vector. So that means from x to a box of x with a subscript b in it. So how do we go back and forth? Well, that's the capital S, right? So now we put in a transformation. So now we have a linear transformation. What happens is this. We have x1, x2 here. That is the domain, right? And then we have a target. This target, I want to make it simple, so we have R2 also. It doesn't have to be, it could be different, right? So there is a linear transformation. So this x has a coordinate system, or just a basis. So when we say have a coordinate system, that means there is a basis, right? So V1, V2. So every vector is mapped to a vector in the target. So this vector, so we begin with x, you end up with a t of x. So x has coordinates relative to b. So we have, say in this case, y, I still use x1 and x2. It is like from R2 to R2. So this basis is used for both the target and the domain. Okay? So Tx has also coordinates, right? T of x relative to the same basis, or the b basis of x and the b basis of Tx. So that's the two players. Before we just say you give me a vector, we talk about its coordinate vector. But now this x is mapped by t to something called Tx, right? So now we want to find a b. We want to find the matrix B. B times the coordinate of x should be equal to the coordinate of Tx. So that is the B we are looking for. So this is called the matrix of a linear transformation. So this is linear. So this is the topic, next topic. It is more technical, okay? We will find this b by 3 different methods. So 3 different methods. Let's go to 4 more problems. In exercise through,
To the bathroom.
No,
you see this?
I gotta leave.
Why?
19 through
My
24.
car.
Find the matrix B.
I forgot my.
Of the linear transformation capital T. T of x equals A times x. So this T is linear, so T is Tx itself without the coordinates, right? Tx is A times x. Okay?
Can you record or stop it?
Relative or with respect to the basis B. This basis B1, B2 is given. So problem 19 through 24 are for R2 transformation explanation. Okay, why we have this formula? But now, in fact, you can already use this method. So as one of the 3 ways to solve those problems. Why? Because they give you the formula. B is S inverse AS. So A is given. The linear transformation T is defined through this A, right? So they give you A, and then you have V1, V2, then you can form the matrix S, right? Well, 2 by 2, you can find its inverse. We have formulas, right? A, B, C, D. So what do? We interchange A and D, right? We put minus sign on B and C, right? And then we divide it by AD minus BC, the determinant. If that is not 0, you get yourself the inverse, right? So you have S inverse times A times S. So even we did not give you a good explanation, right? Or even I didn't have time to give you the detail, you can already use that method. Now, B. Use a commutative diagram. So this is harder. Okay. Commutative diagram, as in examples 3 and 4. So I'm going to work out a problem between 19 and 24. You can pick a number. At
22.
random. Okay?
22.
22.
22.
Why?
Because it came out of my brain.
Huh? 22 is what special about it?
It's all ones.
All ones, okay.
22.
It's fine. I'll work out this. Instead of example 3 and 4,